Hello everyone, my name is Firas Al-Kassar. I am a PhD student at Eurocom University and I'm working at SAP at the same time. It's my pleasure today to present my work. Unfortunately, I'm not able to be with you because of some visa issues, but Luca in the audience and please feel free to discuss with him our work during this event. So today I will present the Testability Tarpits, and this work is between SAP and the Shift Left companies and Eurocom University. So what is a Testability Tarpit? To define that, let me go through an old CVE that's in 2011. Here we can see that we are including a file, while the name of the file is inside this variable. So if the attacker can control this variable, he will be able to control which function, which file will be included, and that will cause a file injection vulnerability. So if we go backward from this variable, we can see that it's coming from the act variable, which is coming from the GPC string function. Inside this function, we can see that we have this built-in function called user_func_array. And actually, this function in PHP will allow to us to call the functions dynamically. Obviously, here we don't need to use this feature because GPC get is defined statically here. But in our experiment, we found this type of feature, it has a high usage. So the GPC get will be called, and inside this GPC get, there's a source, and this source will return from this function. So the attacker here, he can pass a value, and this value will not be sanitized, and will go to the including file. So he will be able to control which file will be included. We test this source code with a static tool, and then we found the tool is not able to discover the vulnerability. We have a doubt about this call user_func_array, and to be sure, we create our testability targets. The testability target is the simplest possible code, that it has a source, the sink, and there's a path between this source and sink. And 4 out of 6 in our arsenal for the tools, they were not able to discover the vulnerabilities. To be sure this is the main reason and there is not another reasons, we transform this pattern and we check again. Sorry, I just want to mention here that we transform the pattern to call the function directly instead of using the dynamic call. So now we scan again the source code and we found that the tool is able to discover the vulnerability. So for static tools, they know the source and they know the sink, but for some reasons, they lose the path between the source and sink. They cannot follow the source until it reaches the sink. For example, here, the tool will not be able to know which function will be called, but when we tell the tool exactly which function, then it's able to have a better coverage. And these reasons that they are interrupting the path, they are our testability targets. So our approach is defined in 3 stages. We create the patterns, we check their prevalence, and we run some experiments for transform these patterns. Let me begin first with the pattern creation. For the pattern creation, we want to show that our approach is applicable for all the languages. So for this reason, we choose 2 different scripting languages, which they are PHP and JavaScript. To create these patterns, we go through the language documentation to the corner cases and to all the discussion inside the pages of this documentation. And we create our patterns from there. And to be sure that we have a good coverage for the language, we evaluate them also by other approaches. For example, we look to the opcode in PHP, which is the 2nd level language. So each opcode is one instruction for PHP. So in our patterns, we were careful to cover all the different opcodes as in PHP. And we create our patterns in different dimensions. For example, if they are features of the language, or if they are internal API, security related, if they are static or dynamic features, positive and negative test cases, functional and object oriented. After creating the patterns, we select them when at least one of the tools is not able to discover the vulnerability inside this pattern. We can see that here we have different dimensions, as I mentioned, and the tools have different behavior depending on the dimension. But at the moment, the most important that is the first column, which is showing the overall the patterns, the behavior of the tool. So we created 122 instances for PHP and 153 in JavaScript. All the targets for the column for the overall targets, we have the best coverage for PHP is 50%, while for JavaScript is 60%. Meanwhile, the combination between the tools, we could reach 66% for PHP and 82% for JavaScript. So after we create the patterns, what if these patterns are not really used in real projects? Or what if they are just a fancy features that no one uses? To answer these questions, we search for the prevalence of these patterns in real projects. And for that, we used Yarn, which is the code query engine that uses the code property graph. And also, we cloned the projects to build the dataset from GitHub. And to be diverse as much as we can, we choose depending on the number of the stars, the popularity of the project. So we create 3 sets, which is not popular, medium popular, and high popular. And also there is this website, the Source Codister, which is offering open source website for the community, is that they have 340 projects that we also add them to our dataset. Here, to check the prevalence, we can see that in these figures, the colors is just depending on the set of the dataset. And in the X dimension, actually, it will represent the occurrence of the pattern every how many opcodes. So for example, here in this case, we will experience one pattern every 20 opcodes. While in the Y dimension, it will represent the number of unique patterns per project. So here in average, we will have 21 unique patterns per project. After that, we focus on the best 2 tools in our study, which they are the 2 commercial tools, to check the prevalence of their patterns. And we can see that for the first tool, that it will experience one pattern every 47 opcodes, and the another one will experience one pattern every 203 opcodes. So even for the commercial tools, they are still having many targets and difficulties to scan the project. And if we are able to solve these patterns, we are able to have a better coverage and better results as an output from the tool. In our paper, we have a long table about the details of the patterns. For example, the dimensions of the patterns, the tool's behavior, the occurrence of these patterns in the different sets from the projects in our dataset. And for example, we can the examples that we already discussed about the call user func array when the name of the function is defined statically. We can see that out of 1,000 projects that they have more than 1,000 stars, there's 208 projects that use this feature with a median of 2.5. So with the motivation of our high prevalence, we apply 2 experiments with the manual and automated pattern transformations. So in the first experiment for the manual transformation, we went to the old CPEs. We check the vulnerability path and we scan the project with the static tool. If the tool is able to discover, if the tool is not able to discover this vulnerability, then we search for the patterns inside this path and we apply the transformation for these patterns in the whole project. We apply is this transformation in the web projects for the vulnerable version of this project and also the latest version. So we chose 5 projects for PHP and 5 projects for JavaScript. We were able to find many vulnerabilities in the vulnerable version, and also we found many vulnerabilities in the latest version. Here it's important to mention that discovering the vulnerability and reporting it and fixing it in the past says there is another vulnerability similar, or they are not discovered because of the same reason, which is a testability target. So if we are able to resolve this target and use one of the static tools, we will have a better coverage for the source code, and we can find a safer version for this project. So as for the manual transformation, while for the automated transformation, we choose 5 testability targets and we apply the transformations for them automatically. We run the static tools before the transformation and after the transformation, and then we check the new alerts after the transformation manually. Here in this table, we can see that for each pattern transformation, we have 5 transformations, so from R1 to R5, and their occurrence and the number of projects that they have these patterns in each set in our projects in our dataset. And here we can see that the number of alerts and the number of true positive out of these alerts that we have. So we refactor around 1,170 projects with an occurrence 32,000. We discovered around 10,000 new alerts in 72 applications, and overall we found 370 new vulnerabilities in 43 applications. Out of these 370, 55 vulnerabilities they are in high popular projects that they have more than 1,000 stars in GitHub. We did all the responsible disclosure and we gained the CVEs for our discoveries. All the details about them, they are in our repository in GitHub. Finally, just to conclude, as we create our patterns, we have 122 instances for PHP and 153 for JavaScript. We found that our patterns they have a high prevalence, that we will experience one pattern every 20 opcodes. And we run 2 different experiments to see the effect of these patterns. We run a manual transformation and auto transformation, and that's allowed to us to define many CVEs and all the details as I mentioned that's in our repository. So please feel free to go back to the repository and check all the details that's in this paper. That's all I would like to share with you today. Thank you very much for listening. Please feel free to if you have any questions now or even during this event, Luca is there and we will be happy to have any discussion with the community. Thank you very much.